page 43. And anytime I change these, they don't scroll correctly. There we go. So we're going to verify them. We did them. We found them yesterday. Today we're going to verify. So this is what goes here. Two functions are inverses if they are reflections in the line what? Y equals x. Good. Okay, so if they are reflections in the line y equals x, then they are inverses of each other. So we're going to verify these two different ways, graphically and algebraically. So we're going to start with graphically. So the first thing we have to do is actually find the inverse. Now, reading the instructions is important here because yesterday we were looking at whether or not they were inverses, right? Some of them, they didn't even have an inverse. We didn't do it. This isn't asking me, does it have an inverse, right? It says find the inverse, which tells me there is one. So if I was to put there isn't one, that makes no sense, okay? Because I'm supposed to find it and verify, which tells me it does exist. So I'm going to set this equal to y. Then I exchange x and y, right? So that becomes 3y minus 6 equals x. Then what do I have to do? Add 6. I'm going to solve for y. So 3y equals x plus 6. Then y equals, now I could put x plus 6 over 3, but I want it, that's not what I would really do here. So what does this become here? When I divide this 3 in here? 1/3. So 1/3 x plus what? 2. So my inverse then, inverse function of x is equal to 1/3 x plus 2. So there is my inverse. Now I have to verify them graphically, which means I need to graph the first one. Well, this graphs is a what? What's it called? Linear. So it's going to be a line. So they're pretty easy to graph, right? I can go to my y-intercept, which is -6. Make a point. My slope is what? 3. So I go up 3 and over 1. Then you use a straight edge. Your ID, just plop it up there on the table. Makes a great straight edge. And draw that line in, like so. So that is the original line, f of x equals 3x minus 6. Then I need to graph my inverse. So my inverse is also a line. My y-intercept is 2. My slope is 1/3, so I can go up 1 and over 3. And then I use the straight edge to draw that line in, like so. The third thing that you have to have drawn on here is your line, y equals x. I would suggest maybe doing them as a dotted line, so it's not just like another line in there, but you do a dotted line, y equals x. And I always forget to say this when we start this. Most of y'all probably won't want to use color, but remember that in your supply boxes, I have matte pencils that are erasable, so they're forgiving, and there's little plastic pencil sharpeners. So if the salmon paper is not great for colors, but if you want to use 2 different colors, you totally can, or you don't have to. But I would make the y equals x dotted so it doesn't get confused with your graphs. Okay, we all good with that? Yeah, absolutely. You just have to remind me or ask me for it, but yeah. Yes, on the tests, if you want to use colored pencils and different, I'm absolutely fine with that. Yes, absolutely. All right, everybody good? Can you see that these are reflections of each other? And the two graphs and the line y equals x should all intersect at the same point, if it intersects that line. Sometimes it won't intersect the line y equals x, but it does here. All right, so let's do the next one. We're going to find the intercept. So, not the intercept, the inverse. Set that equal to y. They're going to change places. So, y cubed plus 4 equals x. And now I'm solving for y, right? So, y cubed equals x minus 4. Then what do I need to do? Cube root. So y is equal to the cube root of x minus 4, which means the inverse function of x is the cube root of x minus 4. So I found my inverse. Now I have to go graph both of them and the line y equals x. So I will start with the original function. This is a what kind of function? Cubic, right? So remember, you have 5 anchor points. If all 5 of them fit on the graph, there needs to be 5 points there, right? Some of y'all did have little issues with that on the test. So your anchor points, the first 3 are just 0, 0, 1, 1, and negative 1, right? So we'll start at 0, 0. The only thing that happens, what's the only transformation that happens? Up 4. So this 0, 0 goes up 4. And that means 1, 1 and negative 1, 1 are just right there with it. No big deal. My next anchor point of 2, 8, well, that's going to go off the graph enough where it doesn't matter. But negative 2, negative 8, when I add 4, will be at negative 2, negative 4. Okay, so those are my 4. So I can get 4 of the 5 anchor points on there. Don't leave this one off just because you can't get the other one, because that's going to help you with your shape. And then this is what my original graph looks like. That's why all that graphing was so important. Now I'm going to graph this. Is this also a cubic? No, it is a cube root. And it's like the cubic that's laying down, right? The first 3 anchor points are the same, 0, 0, 1, 1, and negative 1, negative 1. So I started 0, 0. What's the only transformation that's happening? Right 4. So I'm here, I go to the right 4, make a point. So the same thing happens with the 1, 1, and negative 1, negative 1. They're right there. My other one of 8, 2, it goes off the graph, so I don't have to worry about it. But that negative 8, negative 2 does go to the right 4. So it ends up right there. And then we draw our graph in. Like so. What else do I have to draw? Y equals x. Do that y equals x. And you should be able to see that these are actually reflections of each other, right? They actually reflect in that line. That's the whole purpose of all of that stuff, right? And all 3 things should intersect at the same point, or really darn close, because, you know, I realize that sometimes your curve's a little bit off, but it should be pretty darn close anyway. If it's like way off, there's a problem somewhere. You graph something wrong. Are we good? Everybody good? So we can verify graphically? Yes? Awesome. All right, so let's talk about how we verify them algebraically. Okay, algebraically. So 2 functions. F and G are inverses if f of g of x equals x and g of f of x equals x. So we saw why we have to be able to graph quickly and accurately. And when I graphed those, did I substitute a single point in anywhere? No, it was all about your anchor points and transforming them. So now we're talking compositions, right? That's the stuff that you just turned in. So it says verify algebraically that f and g are inverse functions. So we're going to start with f. So I have to show that f of g of x and g of f of x both equal x. We are verifying, which means they are inverses. Your work is your answer because you're showing how to get there. I know then, since they are inverses, and I'm supposed to show this, that the answer is x. They gave me the answer too. The answer is x. You have to show how to get there, right? That's why showing your work is important, because that's the answer. So f of g of x is equal to f of 2x plus 7, because that's your g of x, right? Then I have to substitute that 2x plus 7 everywhere into f that I see in x. So I get 2x plus 7 minus 7 over 2. Everybody with me? Those parentheses that I put in there, I used them because I was substituting in something that's more than one term. Are the parentheses really doing anything for me? No. So the numerator just becomes 2x plus 7 minus 7, which is just 2x over 2. And what does that become? X, right? Isn't that what I expected, what we were going for? We get x. Then I have to do g of f of x. G of f of x. So it's g of x minus 7 over 2. We don't need to freak out because we have fractions, right? So that becomes, I take this, substitute it everywhere in here that I have an x, so it's 2 times x minus 7 over 2 plus 7. So what happens in my first term there? The 2's cancel out, right? Everybody understands why? Don't be doing weird stuff. All right, so that just leaves me with x minus 7 plus 7, which gives you x. If you work through this and you don't get x, there's a problem somewhere. You worked something out wrong, or maybe you didn't find the inverse right, or something. Okay, everybody okay with all that? Any questions? I'll take that as a no. All right, so number 4. We have a domain restriction here. Really doesn't matter for this because we're just finding f of g of x and g of f of x, but there is one. Because if there wasn't one, then I wouldn't actually have an inverse. But I'm going to start with f. Oh, and I need to answer the question, which I didn't. We need to say that these are yes inverses because we've just showed that. And I know that it wasn't a question like, are they inverses? However, I could ask you, are these two functions inverses? And if you can show me that f of g of x and g of f of x both give you x, and the answer is yes. If you get something else weird, then the answer is no, they're not inverses. Okay. All right, so then we're going to do f of g of x here. That's equal to f of the square root of x plus 5. So then I take that square root of x plus 5, substitute it in everywhere I see an x here. So this is going to be the square root of x plus 5 squared minus 5. Because I substituted it into f of x. Everybody okay with that? All right, so what's the square root of x plus 5 squared? X plus 5. Good, so this gives me x plus 5 minus 5, which is x. Then I have to do g of f of x. So it's going to be g of x squared minus 5. So that'll give me the square root of x squared minus 5 plus 5. Are those parentheses really doing anything there? No? Why you got that weird look on your face? Did I lose you? Ask me a question if you got a question. Okay. Well, and who knows what comes out of my mouth sometimes, so stop me if I do say something weird. So x squared minus 5 plus 5 just gives me the square root of x squared, which is what? X. And that's what we expect. Okay. So it should work out nicely. Like, you kind of know what's going to happen. It should work out just fine. Okay? Everybody good? Any questions at all? All right. Awesome. Flip it over. And we are going to go to number 6. It says, find the inverse of each function, state any restrictions in the domain, verify graphically and algebraically. So we've got 3 pieces here, which is what I'm going to ask you to do on your quiz tomorrow. Find the inverse, verify graphically, verify algebraically. Okay? So it doesn't say if there's an inverse, find it. It says find the inverse, which means there is one. So I'm going to here take this. I'm going to find the inverse, so I'm going to set it equal to y. Then what do? Switch them. So cube root of y plus 2 equals x. So then this 2 is on the outside, which means I can go ahead and move it. Cube root of y equals x, what? Minus 2. Then to get y by itself, what do? Cube it. I'm going to cube both sides, so I get y is equal to x minus 2 cubed. So the inverse function of x is equal to x minus 2 cubed. So I'm supposed to find the inverse. I did that. State any restrictions in the domain. Are there any domain restrictions here? No. A cube root, the domain's all real numbers. Cubic, all real numbers, so we have no restrictions here we have to worry about, right? So now we have to verify graphically. So I'm going to start with the original function, okay, which is a cube root function. And the transformations that happen are what? Up to, that's it. So my 0, 0, 1, 1, and negative 1, 1, those 3 points, there's no stretches or reflections, so it just goes up 2, and there are those 3 points right there. then that 8, 2 would be the next one because it's a cube root, right? So 8, 2 just goes up 2, and I can get that negative 8, negative 2, and move it up 2 as well. So I can get all 5 of those anchor points regraphed. Then my graph. There's the original one. Okay. Everybody good? The graphing getting a little easier? Yes? Remembering your anchor points getting a little easier, right? It's not a matter of memorization. It's just a matter of understanding the picture and what's happening. All right, so then I'm going to graph this one. It's a cubic. What's the only transformation happening here? Right 2. So let 0, 0, 1, 1, and negative 1, negative 1. There's no stretches or compressions, so they just all 3 shift over to together, like so. And then also my 2, 8 just shifts over 2, and my negative 2, negative 8 shifts over 2. So I get this. Then what's missing from my graph? Y equals x. Good. Draw my y equals x. Whew. Mine's a little wonky, but you should have a straight edge with your ID, so you should be able to look a little bit better than mine. Okay, we all good? So I have verified graphically. Do you agree from the graph that these look like they are inverses of each other? Yes, I believe that they are. But even though we're pretty sure now, it still says to verify algebraically. So instead of f of g of x and g of f of x, it's not f and g, it's f and the function inverse. So f inverse of x, that's what that would look like. It's just instead of a g, it's the function inverse, equals f of the inverse here is x minus 2 cubed. So if I take that and I'm going to substitute it back into f of x, that's going to give me the cube root of x minus 2 cubed plus 2. Everybody with me? What's the cube root of x minus 2 cubed? X minus 2. So it's just x minus 2 plus 2, which is okay. Everybody good with that? Yes? Awesome. Then f inverse of the f of x, because I got to do it both ways, right? Got to show that both of them will give me x. This is equal to the function inverse of f of x is the cube root of x plus 2. So I take that cube root of x plus 2, substitute it in everywhere I see an x down here. This is going to give me the cube root of x plus 2 minus 2 cubed. Are those parentheses really doing anything for me? The inside ones. I got 2 sets of parentheses. The inside ones, not so much. Outside ones, they're important, right? So on the inside of that, then, I just get the cube root of x plus 2 minus 2, which just gives me the cube root of x cubed. What's the cube root of x cubed? X. And I'm done. Okay. Everybody okay with that? Ask me questions if you got them. Alex, you got a question? Well, so his question was, anytime you have a domain restriction, the only time it matters is graphically. Well, it does matter when you're graphing it. When you're verifying it over here, no, the domain restriction doesn't do anything. But when I'm finding the function inverse, then the domain restriction matters. And that's something that we're going to look at right here. So it's a good question. So yeah, you don't have to take it into account when you're verifying algebraically. Because it should start, if there is one, it should start with 1. And if it doesn't say that, then you don't even have to verify anything. That's a good question. All right, we good? Anything else? Okay. All right, so then let's look at 7. So we have a domain restriction here, right? It says x has to be greater than or equal to -4. And that should make sense for the most part because when you take this, and if I just graphed this with no domain restriction, if this wasn't here, what's the parent function of that? It's a quadratic. It's a parabola, right? So it would look like this. And then does that have an inverse? Does that pass the horizontal line test? No. So it doesn't, right? That's why we have to have that domain restriction. But there's some transformations here. But they're basic. There's no stretches, compressions, or reflections. What does this 4 do? Goes to the left 4. And then the -2 means down 2. So we basically just take this, and we're going to go to the left 4 and down 2. That's where my vertex would be. And so this is -4 and -2, right? And so this is the vertex. I just get half of the parabola like that. That's why x has to be greater than or equal to -4. Does that make sense to you? So this point right here, this point would be -4, -2. That's why your domain has to be greater than or equal to -4. If I only have half the parabola, then what I reflected in the y and y equals x, I'm good. You with me on that? Okay. So let's find this. And now in actually finding the inverse, I don't worry about the domain restriction. It's at the end I have to talk about it. So I can take this, I'm going to set it equal to y. Then that gives me y plus 4 squared minus 2 equals x. So can I go ahead and take the square root of both sides? No, what do I have to do first? Add the 2. Yes, make sure you're going in order. So y plus 4 squared equals x plus 2. Now what do? Now I can take the square root. So y plus 4 equals the square root of x plus 2. Now, I've made a big deal about when you introduce a square root, you have to put plus or minus, right? Because like in a case like this, if you don't get both parts of the parabola. Do I want both parts? No, I actually don't want both parts here. So that's why I'm not putting this plus or minus here. It's why I make sure you understand. It's not that I forgot it. It's not that I just don't use it for anything like this, but it's because we're only using half of it anyway. Does that make sense to you? Okay. Then I need to subtract 4, right? So y equals the square root of x plus 2 minus 4. And I'm just going to go ahead and put that's equal to the function inverse of x, so I don't have to rewrite it again. So there's this. But then we got to talk about the domain restriction. Is there going to be one? Yes, it's not all real numbers, right? Before I did any of this work here in blue, should I already have known what my domain restriction would be, and how would I know that? How do I know that from my original one? What switches? The x and the y change, so the domain and the range change, right? So for this one, this is my domain, right? The range for that, the range would be that y has to be what? What's the range here if this is my point? Greater than or equal to -2, right? So this is your domain, this is your range. So since x and y switch places, they switch places here too, right? So your domain here is not that x has to be greater than or equal to -4. It's that x has to be greater than or equal to what? -2. Which should make sense when you see what's happening here, right? There's your domain. Okay? So you can find it all from the original, and then the domain and range switch places because they are your x's and y's. Everybody okay with that? All right, so now we graph. So now I'm going to start with the original one, which is a parabola, but it's only half of it, and we kind of got the idea over here anyway, just to talk about it. And since you had to graph it anyway, if you weren't sure about the domain, go ahead and graph it, then figure it out so you don't have to go by a little sketch. There's nothing wrong with that since you have to do it anyway. Remember, no stretches, compressions, or reflections, just translations, so that makes it easy. So when I start here at 0, 0, I go to the left 4 and down 2. So that means that point, my anchor points here, there were 5 of them, but I'm not using all 5 because all my x's have to be greater than or equal to -4. So 1, 1 is going to go to the left 4 and down 2. And then 2, 4, I'm going to go to the left 4 and down 2. So those are the 3 anchor points. The other 2 are not in my domain. So this is just the half of the parabola that I would get. Everybody okay with that? Able to graph quickly and accurately is very important. So then this is the square root function, right? How many anchor points do you have for your square root? Just 3, right? So 0, 0 is one of them, right? Because your square root looks like this. Hopefully we know that. So we start with 0, 0. This, I'm going to do what to it? left 2, and down 4. So start at 0, 0, to the left 2, down 4. My next anchor point for a square root would be 1, 1. And from there, I would go to the left 2 and down 4. Where's my next anchor point? 4, 2, good. So I would go to the left 2 and down 4. And then it looks like this. Missed a little bit. Okay, everybody good with that? What's missing from my graph? Y equals x. So I graph in y equals x. And those are reflections. My y equals x is off just a little bit, so if it was actually where it was, it would look a little bit better. If you got a straight edge and an ID, you can plop it up there and get it exact right, please. Okay, we good? Any questions at all? What do we have to do now? Algebraically. We got this, right? So I need f of the f inverse of x. This is my inverse here. So I need f of square root of x plus 2 minus 4, like so. So that square root of x plus 2 minus 4 gets substituted into the f up here, and that's going to give me the square root of x plus 2 minus 4 plus 4 squared minus 2. So all that stuff in there, make sure you understand where everything came from. Everybody good with where everything came from? So this set of parentheses, not really doing much, it was just grouping that. So square root of x plus 2 minus 4 plus 4 is just going to be the square root of x plus 2 squared minus 2. So what's the square root of x plus 2 squared? X plus 2. So x plus 2 minus 2 gives you x. Is that what we expected? Yes, that's a good thing, right? So then I have to, so when you're doing things that you don't really like square roots and they push you out of your comfort zone, when you know what your end result is, you know it's going to work out just fine anyway, it makes it not quite so scary, right? Because you know what to do with these. I know you do. So the function inverse of the f of x is equal to function inverse of x plus 4 squared minus 2. So I'm going to take that, substitute it in everywhere in here. So this is going to be the square root of x plus 4 squared minus 2 plus 2, all that's underneath, and then minus 4. So I got a couple sets of parentheses. These matter. These here, not so much. So this square root of, x squared plus 4, x plus 4 squared minus 2 plus 2 just becomes the square root of x plus 4 squared, because that minus 2 plus 2 zeroes out, minus 4. What's the square root of x plus 4 squared? X plus 4. So x plus 4 minus 4 gives me x. Verifying, right? I know that y'all may have not done a whole lot of verifying, but when you're verifying, your work is your answer. Can you skip some steps? Yes. But you can't just say, I know it equals, I can't just put this equals x, because how do you know? You have to show me. That's the whole point, okay? Are we all good? Any questions? Y'all got it now? Yeah? Okay, good. I don't think we need to do the rest, but I will tell you that here, I just want to talk about what this parent function is. What's this parent function? It's a reciprocal, right? And so when you graph it, it looks something like this, right? So when you end up having to graph two of them on there because they're reflections of each other, you're going to have two sets of asymptotes and two sets of these little curves, so there'll be a lot of overlap, and that's okay. Don't let the overlap freak you out because you think something's wrong. Okay, we all good with that? Any questions at all? Awesome. And I'm going to give you some time to work. But if you have a question, ask me.